Contemporary. And like that. Okay, so after Full Tempore, and if you have already opened the buffet, something like so you don't have to get up. Welcome to the SIG26 Knowledge Wheel of the Vienna Data Science Group. In short, Vienna Data Science Group is a non-profit. That means we are more than a meetup. That doesn't mean meetup is bad, but we are just doing a bit more than this, like workshops, seminars, writing books, and so on and so forth. But I think a lot of you already know that. So today we have two very different speakers. First, somebody who will tell us about smart cities, and Vienna already thrives to be like that, I heard. But I don't know if you talk something about Singapore, maybe. Sometimes they say they are in the forefront. Second thing is, what are we doing with all these privacy and deep learning? I think mostly AI has a quite interesting approach to that. So let's hear that. I think you were recently, you got funding, right? Yeah, cool. So kudos to you. And that's it from me, because I'm pretty sure you're much more interested in what is coming than me speaking. That's it.
Hello everyone. Good evening. You can see from my face I'm an Indian guy. In India, when we say good evening, good morning, etc., we normally expect the people also to reciprocate. So let's say good evening again. Good evening. Oh, there you go, okay. I'm going to talk about smart cities today from the perspective of deep learning, from artificial intelligence and deep learning. Next 45 minutes, I'm going to talk about a bunch of use cases and the solutions, how we can solve the smart city challenges. And then we have another 10-15 minutes, I think, for Q&A. Before I start, I want to just clarify that, being an Indian guy, I talk very fast, and if you have any difficulty in following my language, please let me know, I'll slow down. And my wife tells me, by the way, my wife is sitting right there in the audience, and she tells me all the time, don't talk so fast, just slow down. People are like, this will not understand what you're talking. But I have so much of material to talk about, so I want to really communicate whatever I want to. Smart cities, there's a lot of cities trying to solve some of the challenges. When I say a smart city, it could be a city which actually has 5 to 10 million population or even more. If you have more and more population coming to the country, into that city, you have to use certain additional technology to keep the society and the city, and also address some of the requirements of the city itself because of the population. We in Hexagon, we have been working on smart city solutions, but I will not talk about what we are doing in the company, but I'll talk about some use cases. When you say smart cities, you talk about the traffic, tracking the traffic, or taxi demand prediction and similar things. There are so many other smart city use cases where people have already solved issues like, for example, in the United States, which restaurants inspections need to be prioritized based on so much of information available. And the use case looks very complicated, but it's a very basic machine learning, not even deep learning, machine learning solution of 11 parameters used to detect and prioritize which restaurants need to be inspected. And of course, there are similar use cases. Land use classification. What type of usage this land is being used for is also used for using deep learning. Clean Streets program, you can also use that. This is the most interesting for me. There is a deep learning model which is implemented in certain cities in the United States, which can detect the sound of gunshots. Among all the noisy environment, if there is a gunshot, there is a machine learning deep learning solution which actually can detect and alert the security agencies. And there are similar use cases too, but we in Hexagon are developing a platform called Exalt, which helps in collecting data, aggregating the data, and applying a bunch of AI solutions on it to make sense out of the data. But what are those use cases? You know, in this today, even though I've given presentations in multiple places, the screen is right behind me normally. So people, even though they're looking at the screen, I do feel that they're looking at me. But today the screens are right up on the roof almost, as I don't get the impression that you guys are listening to me. So do once in a while look at me too. I know you're looking at the screen. But for the next 4 or 5 slides, I'll get into the details of specific use cases. These use cases are published papers, and I would explain each of that. Even though in this case, there are a bunch of use cases here, let's talk about the first use case. If you have a smart city, let's say like a Vienna, and if you have a surveillance cameras, how many surveillance cameras are in Vienna, do you know? Thousands, let's say 5,000, 10,000. So if you have 10,000 cameras, every 1 hour there are 10,000 hours of video that's coming in. How would you manage such amount of video? A couple of years ago, before deep learning really picked up, there was a brute force approach where you transmit all the video into a central server, see if you want to process it. If you cannot process it, just keep it that way for the legal requirement of number of weeks or months or years, and then delete it. The current approach is dual approach. One is, can we do an intelligent compression of the video and send it to the server, but also can we do edge computing, where you can have an AI model sitting on the edge device, in this case a surveillance camera, which can process on what is happening. I do have a few papers in the next few slides which talk about how do we process the video and identify maybe the actions, what's happening in the video. But before I get into the use case, in this paper, by the way, every slide or every paper I talk about, the link to the paper is at the bottom of the slide. You can go back and read more information. And in the next 45 minutes, I'll not be able to cover all the details of each paper, but I really want to get this information across to you about how these use cases are solved. The 4 most interesting, challenging use cases in a smart city is face re-identification, vehicle re-identification, and a couple of others, but I will talk about face re-identification. Why is face identification very difficult, even using artificial intelligence? You all have used Facebook? Yeah, you use Facebook or Instagram? Yes? No? If you have used any such social media application, and if you have uploaded your picture, the AI model knows who you are. Next time the model sees any image or any picture where you are located, it can easily detect where you are. That's an easier problem solved already. But imagine a situation where in a city of 1 million people or 5 million people, some of them actually are tourists who are coming from outside into the city, let's say in Vienna. And do you want to find out a person who was spotted on a Monday morning by camera 123, is it the same person which was spotted in a different location in the city by a different camera, where the person looks now different, or the dress, or even the facial, maybe the hair, for example, is all changed? Face re-identification is an extremely complicated problem. And there are, in 2016, I've seen a paper where it talks about triplicate loss. An AI model is trained using a training data set where images of the same person, but they look different, and image of a third person who's extremely dissimilar would be fed into an AI model, and you train the model to tell the difference between similar images and dissimilar images. That's called triplicate loss. And I'll show some of those videos, some of the solutions. But before that, let's talk about detecting cars in parking lot. If you have a satellite image, and if you want to find out just the cars, not the roads, not the buildings, not the delivery trucks, but just the cars, because you want to find out number of people who have come into your store. If you want to find out the traffic that's coming into your store. An image which is shown there could be, let's say, 500 by 500 pixels, or it could be even sometimes 1000 by 1000, which is rare. Normally satellite images are not that high clarity, maybe 250 by 250. In an image of 250 pixel by 250 pixels, the size of a car could be anywhere between 10 pixels to 20 pixels. Identifying where the car is located. This is a paper published in 2016. They primarily used a model called YOLO. Have you heard of YOLO? You only look once, not the other YOLO. This is an open source code if you want to use this model to detect objects. YOLO 1 was a little slower model which could detect at the rate of 40 frames per second. YOLO 2 and YOLO 3 actually include can detect objects faster pace, even at the speed of 220 frames per second. So we actually can use YOLO on an autonomous car driving on the street, or autonomous, let's say, a drone flying can detect the objects and classify the objects too. This is a very simple YOLO 2 implementation. If you look into the architecture, I'm assuming you guys are familiar with CNNs, convolution neural networks. The architecture is a plain, simple convolution neural networks of multiple layers. You have the input layer and you have the conv layers, and towards the end you have a couple of fully connected layers, and the last layer is when you do a classification using YOLO 2. This model is around 90-95% accurate and can detect all the cars, and the use case is detecting the number of cars that's coming in. Unconfirmed reports say that Walmart in the United States wants to use this model, or maybe they've already been using, to detect the number of people coming in into their various stores based on a per hour, per week, per day, and find out the correlation between the model output with their own supply chain information. And maybe there are other companies and other government agencies trying to use this, but the simple solution is using a bunch of convolutional neural network layers. You can detect, you can do a classification of objects using YOLO 2. When you use any image processing models, one of the biggest problems for AI scientists is annotating it. You have to spend a lot of money and time in the training data set to identify various objects and then train a model. So annotation is really extremely expensive. Here is a solution where, using weak supervision, you can train a model that can identify salient objects. When I say salient objects, let's say you take a picture of maybe this building. You want to only detect the chairs or the tables, or you want to detect only the walls or only the windows. You can train a model where you take images of objects, train the model on the objects, and feed that information to another model which will take that as a weak supervision and then can identify the salient objects. This model actually was a huge leap in the AI circles, where with less annotation, or actually zero pixel level annotation. Annotations actually could be done at the object level, but this was trained based on object level identification, not pixel level annotations. So in this case, again, if you look at the architecture wise, it's a bunch of convolution layers and then fully connected layers, but taking a raw input, you can train a model which can detect salient objects. For example, if you want to detect only cars or only human beings. In my company, we have designed a solution for Industry 4.0 which can detect human beings, unauthorized human beings, in a factory location, let's say in the middle of the night. If you're not supposed to be a human being there, the model will be watching constantly the location and detect a person. And this can be both lighted conditions or it could be dark conditions too. We have both the cameras, the RGB cameras and also IR cameras, infrared cameras, can detect a human being who's not supposed to be there. It's a similar approach where we don't want to detect any other object but just want to detect a human being. And this is the approach. You can read more information about that. The most common use case in a smart city solution is predicting the demand of taxis. Of course, after Ubers and Didi in China, the taxi hailing mechanisms are coming in and they're trying to predict the demand. If you are a machine learning expert, any demand prediction is always done using time series solutions, time series data points. But time series will only talk about, which is not deep learning, only machine learning you can use. But time series talk about information over a period of time which has a few factors influencing the time series. One is just the regular flow of traffic, but also sometimes there could be spikes because of, let's say there's a rain, or maybe there's a music concert, or it's a holiday. Also you have the seasonality. Let's say every Sunday morning there will be hardly any traffic, but Monday morning there's going to be huge traffic. You have a seasonality. It could be a weekly seasonality or a monthly seasonality. In this paper, authors not only looked at the time series part of the information, but also looked at the temporal part, temporal and spatial context too. For example, if you take a satellite image of, let's say, Vienna Museum, take the satellite image of the palace, but also take a satellite image of a university, which is not working on a let's say a weekend. The spatial image shows there's a heavy traffic on a weekend for the museum and for the palace, but hardly in the university. That information is also fed into the CNN model, and the embeddings are extracted and eventually fed into RNN. RNN would actually take the temporal aspect of it. RNN stands for recurrent neural networks. There are variations of RNNs that exist today in deep learning. This paper actually talks about taking LSTM, the variation of RNN is LSTM, long short-term memory. So let me show you this. If you look at, you have the raw images that's coming in, and they go through a convolutional neural network architecture and go through a fully connected layer, and you extract the embeddings. And those embeddings are fed into a RNN, which now becomes a temporal aspect. And then you also have embeddings of the spatial context, trying to take a physical image of a location and then fed into that. And the embeddings in both the models are concatenated and do an end-to-end trace. How many of you guys are familiar with the deep learning terminology like end-to-end training, or CNNs and RNNs and LSTMs? Want to raise your hands? Okay, thanks. Not too many people, but I think deep neural networks, DNN, throwing in a lot of terminology here. DNNs, you have a variety of neural networks available. For any type of use case that takes a series of information based on time You normally use a recurrent neural network or an LSTM or a GRU to process that information. Second rule of thumb is if you're processing images, it could be a still image or a video, predominantly 2D images, not 3D images. There are some problems if you use 3D images for this solution. But for image processing, you use a technique called CNN, convolutional neural network. That's a different type of neural network which actually understands an image and figures out what is in the image. In this paper for taxi demand prediction, because it's not a time series problem alone, authors have taken a combination of CNNs and LSTMs to make a classification of where the demand is. I mentioned earlier about phase re-identification. Any smart city solution, if you look into even some of the Asian countries, I know Alibaba has a couple of implementations already in a few cities, and I think in Thailand. Also, there are a few European cities and maybe in the United States too. They have smart city implementations done. For example, Hexagon, I don't know about Europe, but I think in the US, we have this 911 call system. For emergency services, you have cops or medical services coming in, we call it 911 system. Good number of cities, when someone calls 911, the technology is supplied by Hexagon. I need to still find out about which European cities we do it. But person re-identification is one of the difficult aspects, but it's also being done more and more by the cities because you want to identify who the people are, but you can't force everyone to sign up and give the names up front. So a couple of years ago, the paper published, or the solutions were more of triplicate loss. If you want to train a model, take 2 images of the same person and a third image of an entirely different person. Tell the model, image 1, image 2 are of the same person, image 3 is a dissimilar person, and then you do a training. That's called triplicate loss. One of the problems of triplicate loss is you got to tell the model, or you got to give the images in a sequence.